Hello students, today we are in lecture number 10. Of chapter 1. Electrostatics. Students, we'll start today with the topic electric line of forces. This is B.S Pandey. Student, in your course you have to study after the electric field about the electric line of forces. Okay, and this is also called electric field lines. Electric field lines. Students, actually electric field lines is an imaginary line that we use to draw, which extends or which gives the path of extension of strength of electric field. That is a charge which influences other charge particle. So this electric field lines gives the path, and it is imaginary. You cannot touch it. Okay, so it is imaginary. When we talk about the properties of electric field lines, as we have been studied, this is electric field lines, imaginary lines. Remember the one thing, it may be a straight line, or curve. Okay, it may be a straight line or curve. If a student, the source of this electric field lines is at very large distance with respect to the observer, it means the charge, any other charge, then usually we get the electric field lines as a straight line. If the two charges, like charges or dislike charges, kept near to each other, electric field lines usually finds curve. Okay, student? It is assumed that for the positive charge, the electric field lines or the positive charge are the source of electric field lines. That is, electric field lines emerge out from the positive nature of charge. Where it goes, as you can see, this is the straight line, this is the straight line. Of course, it is going to infinity. No doubt, it is going to infinity. If we'll put a charge near this positive charge, it might be the number of field lines will curve to meet that charge, or the number of field lines will curve to get repelled by that charge. This is positive charge, and it is assumes that negative charge accept the electric field lines. This is the acceptor of electric field lines. From somewhere these electric field lines are coming. Of course, you can see I have been drawn here the straight line. Again, you will say that, sir, it is coming from infinity. Of course, if I have been drawn this is as a straight line, then it is coming from infinity. Now, you must be eager. So, what will be the structure of field lines if we draw electric field lines for two charges? That is, for the combination of charge. No doubt. So, let me draw electric field lines for the combination of charge. If it is positive charge, it is negative charge. Remember, students, we haven't studied, it is the imaginary line. From positive charge is emerge out, for negative charge is goes towards the negative charge. As we have been discussed in previous lecture, if you would like to find the direction of electric field, that is the electric field lines, since this electric field lines extends the strength of electric field of any charge, if you will put a point charge And what was the nature of point charge, student? Actually, the test charge, it should be the very small in magnitude, and nature should be positive. So it will move if you will put a point charge, that is the test charge. If test charge it is plus, it will move toward this one. That's why we have been drawn here the direction of electric field towards the negative charge. If you will put positive charge, that is the test charge, it will move away. That's why we have been drawn here the direction of field for the positive charge away from it. Now, for the combination of charge, if we are having a system in which we are having two charges, remember students, I am taking here the two charges of same magnitude. If it is 5 coulomb, then it is 5 coulomb. If this is 2 microcoulomb, this is 2 microcoulomb. Okay, so the field lines will immerse out and it will complete to the negative charge. It will move from here and goes to the negative charge. What will be the shape of the next field lines? So if there were no negative charge, it goes infinity, but here the negative charge, and it will start attracting this field and it will move towards the negative one. So you can draw now this as the direction of electric field lines. So this is the direction of electric field lines, my dear student. Now we can put the direction for each electric field lines. It is this one. Remember, while drawing, you must have to bear in your mind that the direction of each field lines in such a way that two field lines never intersect each other. So this is the direction of field lines, or the shape of field lines for combination of charge in which we have been taken the two charges of same magnitude but opposite in nature. Now I know that you were thinking about, so what will happen if we'll take two charges of same magnitude but of same magnitude and same nature. Okay, so let me draw here the field lines for the two charges of same magnitude and same nature. Of course, this will leave the field lines, this will also leave the field lines, but this field lines will not compete with this charge because both are the donor of field lines. What will happen? They will approach and at certain distance start repelling each other. They will approach, and remember, since both the charges are of same magnitude, so they will approach for the same distance. The distance this line will move, this will also move for the same distance, because these are the two. You can draw better. Here I'm just giving you the concept, and the concept is this one. The two charges will produce field lines in this way. Okay, in this way. Now the field lines away, this is away and this is away. Remember, this line is going to be continue, but it will not intersect each other. This line going to be continue, but it will not intersect each other. Okay, this will not intersect each other. What about this point or the space? Actually, this point is called neutral point. This is called neutral point. Neutral point. So in this way, now you can also draw the electric field lines for the two charges of same magnitude and same nature as negative. You can draw the field lines. I know. Now students, the next example. So what will happen if we'll use two charges of same magnitude, of different magnitude and same in nature? Okay, suppose it is Q1 and it is Q2. Okay, both are positive. Here Q1 and Q2 are positive. What we are taking, actually the condition is Q1 is greater than Q2. Okay, Q1 is greater than Q2. So the electric field lines will extend actually for both the charges, whatever may be the magnitude of the charge, for both the charges and for all the charges, the electric field line extend up to infinity. Electric field lines extends up to infinity. But since this charge Q1 is dominating with its magnitude, so it will dominate over the field lines also. So the field lines will be in such a way. The field lines of this charge between this way. Again, these two will not intersect. Remember, these two will not intersect. So in this way, the field lines will be there. This is the structure of field lines. You can see for this charge, that is the Q1, which is higher in magnitude, its electric field extend by the last distance and it goes near the Q2. Okay, and again this will be the neutral point. The neutral point will be near the smaller charge. Okay, near the smaller magnitude charge. This will be the neutral point. Since both the charges are positive, so the field lines will be outward. Both are the donor of field lines. Now you can draw the diagram. So this was the actually concept. Okay, students. Now let us consider few important points as and you should note down as a property. Okay, remember students, here I have been drawn this electric field lines by mistake. Otherwise, if this is the point charge, then you must will represent the point charge, the field lines, it should be the perpendicular, okay, at each point. Now let us take few property or the important points about the electric field lines. Important points about the electric field lines or the electric line of forces. Okay, the density of electric field lines, actually defines the strength of electric field. Remember, kindly note down, the density of electric field lines defines the strength of electric field. Remember, for example, suppose this is the electric field lines. This is the electric field lines and the source is somewhere and the field lines are coming. Of course, this will be considered as a non-uniform electric field. Non-uniform electric field. Non-uniform electric field. You can write in complete word. Now, let me take the 2 points, okay, A and point B. Here, remember students, point A and B, it is very easy to see. You can see the density of field lines. Here the field lines are converging and the density is increasing. So the high density, why this density has been increased, it totally depends upon the charge, for which charge it is going to be meet and what is the nature of the charge actually. Okay, so here the density of field lines you can see is larger. Here the density is smaller compared to this point. That's why we can write here the strength of electric field at point A will be smaller than the strength of electric field at point B. Actually, this concept I was explaining you, the density defines the strength of electric field. Here the density is larger, that's why the strength of electric field lines will be higher. In case of, if the question is coming in your mind, say in case of uniform electric field, what will happen? Uniform electric field, what will happen? Okay, so if this is uniform electric field, remember uniform electric field must be represented as a straight line. This is the uniform electric field. Remember, uniform electric field. In case of uniform electric field, this is the uniform electric field. E other point, 2 points we are taking here, the point A and point B. Here the strength of electric field at point A is equals to the strength of electric field at point B in case of uniform electric field. Okay, so the next property, student, electric field lines actually moves from higher potential. We will study in detail about the electric potential and potential energy, but try to remember, try to make your notes that electric field lines move from higher potential to lower potential. This type of question will be asked in your board examination. Okay, so if electric field is moving in this way, here the point A and point B, and this is nothing but the electric field lines. So you can write easily, if electric field lines moving from A to B, electric field lines moving from A to B, and we know that the electric field lines moves from higher potential to lower potential. So we can write here the potential. If V is the potential, V is the potential, then potential at A, which potential actually we are talking about here, the electric potential. Okay, which potential? Electric potential. So the potential at point A will be higher than potential at point B. It is clear? Electric field lines move from higher potential to lower potential. Okay, now the next property, the direction of electric field lines, if if we are having the electric field lines imaginary, if we have been drawn and we are having the direction of electric field lines, then we can find the electric direction of electric field over that or using that electric field lines. Okay, if this is the electric field lines, try to understand, this is the direction of electric field lines. Okay, electric field lines or the electric line of forces. If we want to find out the direction of electric field over here, direction of electric field over here and over here will not be same if it is not a straight line. This is non-uniform. Then direction of electric field can be obtained by the help of tangent. Remember, tangent. So we can draw here the tangent, this one, and this tangent, this is the tangent. Tangent will give you the direction of electric field. Try to make your notes. Direction of tangent gives the direction of electric field. Now the next point, this will help you to explain few important topic. Okay, students. Now the next property is two electric field lines. You have been studying from your standard 10th course. Two electric field lines never intersect each other. Two electric field lines never intersect each other. What does they do not do actually? This is the two electric field lines, and these two will not intersect over here. Why? If the two field lines will intersect at this point, try to find out what are maybe the number of charges we have been studied. If we are having the two charges here, one charge, two charge, three charge, if we wish to find out the net field here, the q1, q2, q3, okay, and we wish to find out the net field at this point, E net, you know, here the charge q1 will produce a field, q2 will produce a field, and q3 will also produce a field. But here we cannot have the individual field by this all charges. We will have the net field, and at this point, if these two lines intersect, then what will happen? For this electric field lines will have the tangent in this direction. Okay, so the tangent 1 and another tangent will have in this direction, tangent 2, Now we can conclude if there are two tangent, then here there will be two direction, and we know that for one net field there must be one magnitude and one direction. Then how is it possible that we'll have the two direction at a point? It is not possible. That's why we are taking it is impossible to intersect two electric field lines at any point, because net electric field cannot have two direction at a point. Okay, so kindly note down, and you can write in your own language whatever you want. I'm writing it. Two field lines never intersect each other. Now suppose, student, we are having a conductor. Okay, we are having a conductor in this way. It is positively charged conductor. It is conductor. So remember, the field lines always perpendicular. Field lines always perpendicular to the conductor. Electric field lines must be perpendicular to the conductor. This is the 90-degree everywhere. If it is positive, then the direction will be in this way, outward. And the second point that you should remember, I'm not representing here the electric field inside the conductor. It is the hollow conductor, and I'm not representing the electric field inside the conductor. So I will discuss in detail when I'll teach you the Gauss law. But here try to remember that the conductor, inside the conductor, if it is positive charge, here the Q net inside must be 0, and if there is no net charge, net electric field will be also 0. So this is the concept. The electric field inside the conductor, closed conductor, must be 0, and the net charge also 0. It was well explained by Gauss, Carl Friedrich Gauss. We will study in Gauss law why this net electric field becomes 0 inside conductor. Now if the question is coming in your mind, students, sir, what will happen if we'll put a charge inside the conductor? Of course we can put a charge. What will happen, sir, if we'll put individual charge inside the conductor? So can we have a net electric field, because now we have been put here the charge, extra charge? So can we have the net electric field, sir? So the answer is no. Again the net charge will be 0. And how? I'll explain you in the next topic, and that would be the Gauss law. Okay, probably. Now the next thing, could you draw the electric field line, student? The one important thing you have to remember, the electric field lines over the conductor should be perpendicular to the surface of conductor. Okay, take suppose this is the shape of conductor. Okay, this is not the symmetric like this one. So this is the conductor. Now what will be the direction of field lines? If we are drawing here the direction of field lines, this is the positively charged conductor. Here I should not mention the positive charge inside the conductor, but outside the conductor. Okay, I'm not drawing everywhere, the diagram will be blurred. Okay, so the field lines will be in this way. What will happen if we'll draw over here? Of course perpendicular to this one. Over here, of course, this will be perpendicular to over here, but it will not intersect each other, remember. And here this is perpendicular, and here this is also perpendicular. In the same way, you can draw the electric field lines anywhere over this type of conductor also. Okay, now I'm giving you few more examples to draw the electric field lines. Okay, student, suppose this is seat, charge seat, positive. and this is negatively charged sheet of finite length. It is not going to infinity. It is not going to infinity. It is of finite length. Suppose 2 meter, 1 meter, 2 meter, 1 meter, whatever. Okay, this is positively charged and this is negatively charged. Then what will be the shape of electric field lines between these two? Try to draw by yourself. Okay, students, look at here. The direction of field lines. This way. Okay, from positive to negative. Now, another example. Again, I'm giving you the two charge sheet. This is positive and negative, but this is going to be at infinity. At infinity. Okay, the two charge sheet of infinite length. Now, what will be the shape of electric field lines? Try to draw if you can. Now, look at here. Here, a little bit curve. Curve will be lesser, almost straight. Curve will be more lesser, almost straight. As will move, it will be straight and straight and straight. So this will be the shape of electric field lines for such type of system. Another example, student, if you can draw. Two charge sheet. Okay, this is positively charged sheet and this is negatively charged sheet, and here I will place a conductor. Okay, conducting sphere. Conducting sphere. Now this is your homework. Actually, I'm giving you this is as homework. You have to draw the fill lines for this system. The fill lines between these two plate sheet, and this is the conducting sphere. This is the hollow conducting sphere, student. So student, this is all about today's lecture. We'll discuss about the electric dipole in next lecture. That would be the very important for board, and we'll find the electric field due to that dipole, students. Thank you very much.